Infinity is weird. In our everyday lives, we don't really encounter infinite things. By all means, what we call infinity might not exist in the real world, but it exists in our minds as an idea. It has sparked philosophical discussions and created paradoxes for thousands of years. Infinity might seem intuitive to you at first, but you'll quickly arrive at unintuitive results if you want things to stay consistent. Today I want to show one specific instance of such a result involving ever-expanding sets of natural numbers. I will try to build up everything we need from scratch so that even someone who hasn't had any previous exposure to things like set theory can appreciate the weirdness of what's happening. Let's start at the beginning. Before we can define what is infinite, we must first define what is finite. I will retell a story by mathematics professor John Baez in his column This Week's Find. Long ago, when shepherds wanted to see if two herds of sheep were the same size, they would have to physically line up both herds and try to map each sheep in one herd with the sheep in the other. If they mapped 1 to 1, this meant that the herds had the same size. If there were sheep left over in the second herd, that meant that the second herd had more sheep, and vice versa. But one day, along came a shepherd who had an epiphany. She realized one could take each herd and set up this mapping, but instead of using another herd of sheep, she used a set of abstract objects she called numbers, which were just nonsense words like 1, 2, 3, specifically designed for this purpose. By comparing the resulting numbers, she could show that two herds had the same size without having to explicitly line them up. Thus, the natural numbers were born. Of course, nowadays we recognize this process as counting, and this one-to-one mapping of sheep is called a bijection, and it can be done between any kinds of objects, be it apples, pears, or numbers. In maths, we usually call our collection of object sets. So what the shepherd basically said was, what if instead of comparing sets to each other, we use our measuring tape, the set of natural numbers, with which we can work more easily afterwards. Okay, but how exactly do we map a set of 5 sheep to the number 5 in a one-to-one manner? Remember, we want to keep this property of a bijection. With two herds next to each other, we can just draw 5 arrows between the 5 pairs of objects. But if we just put the number 5, one would imagine that all 5 arrows collapse on the number 5. Here, we don't have a one-to-one mapping because all the arrows map to the same object. The way this is done is we actually define the number 5 to be the set of all the numbers less than 5, including 0. Now we have 5 objects to work with and we can easily do our bijection. Similarly, the number 6 is the numbers 0 to 5, and so on for every number n. It's defined as the set of numbers from 0 to n-1. Here we see why taking 0 as part of the natural numbers is useful. In this way, every natural number represents some sort of canonical set with that many elements in it, and every other set which contains the same amount of elements can be mapped with a bijection to our natural number. You might ask, what about 0 itself? It has to be some set with 0 elements. We have a special name for this set, it's called the empty set, and it's denoted with this crossed out 0. It's the special set with no elements in it. Now we can say that a set is finite if there is a bijection between it and some natural number. Immediately it follows that the set of natural numbers itself is not finite. There is no cutoff point we can choose to fit all the natural numbers before it. There will always be more after it. I'm sure you can think of many more infinite sets. For example, the set of all integers, which would involve the negative numbers as well, or the set of all possible strings of letters, the set of rational numbers, the real numbers, etc. Let's now explore the infinite sets themselves. We want to continue the idea of bijections, but this time with infinite sets. This part has already been explained in many other videos, some of which you see on the screen right now, but for completeness I'll go over it here as well. Feel free to skip ahead. Constructing a bijection between two infinite sets is not necessarily difficult. For example, let's take 2 copies of the natural numbers. A bijection between them is trivial. But we can also do the natural numbers and the negative numbers. we can just map each number to its negative counterpart. But infinity lets us do funnier things. Let's go back to two sets of natural numbers, but now let's get rid of the number 0 in the second set. Now our first arrow has no corresponding endpoint. But no worries, I'll try to fix this by moving it so that it points to 1. But now we've lost the property of a bijection. The two arrows point to the same endpoint. It's not 1 to 1. Okay, let's try to continue to fix this by moving the second arrow to point to 2. Continuing this logic to infinity, we create a bijection by just mapping each number n to n plus 1. A bijection between two sets tells us that they have the same size, or as we say more formally, cardinality. So in this case, it seems that these two sets have the same size, even though the second one clearly has one element less. This may seem strange at first, but if you agree with the fact that infinity minus 1 is still infinity, then it's probably not so strange. Some of you may also recognize this as Hilbert's hotel paradox, just expressed with numbers. In fact, we can remove any finite number of elements from the second set and still create our bijection by just moving our arrows even more to the right. But what's even more interesting is that we can remove an infinite number of elements and still have infinitely many left. The easiest example is taking the odd numbers and removing them. It seems like we're left with a set that's half the size as the original. But again, a bijection can easily be constructed by just mapping each number n to the number 2 times n. Let's try another set that's constructed not by removing infinitely many elements, but by adding them. I'm talking about the set of rational numbers. Those were the numbers that could be expressed as a fraction between two integers. So for example 1/2 or 4/5 and so on. These numbers seem to be much more than the natural numbers, but interestingly we can still do a bijection. The way this is done is by writing out all the rational numbers in a table which has infinite rows and infinite columns. The index of the row shall denote the numerator and the index of the column the denominator. Each row or column by itself could easily be mapped to the natural numbers, but how could we possibly map the whole table? The trick is to go in a diagonal fashion like this. Continuing this to infinity, we will map the whole table, and we can count the order in which we pass the rational numbers by following our diagonal line. In general, sets that have a bijection to the natural numbers are called countable sets because we can count them. So now the question is, are there any uncountable sets? Up till now, all the infinite sets we encountered were countable. The answer is yes, there are, and the prime example is the set of real numbers. Here it's a question what a real number even is. Some of you may have intuition or know something about it, but in general, the definition of a real number itself is not a simple question. But here I'll use the idea that the real numbers are the rational numbers combined with the irrational numbers, which we'll think of as numbers with infinitely many digits after the decimal point. So for example, pi or square root of 2. And what's more is that there is no pattern in their digits. For example, 1/3 also has infinitely many digits after the decimal point, but it's just a repeating tree. So how do we show that the real numbers are uncountable? Well, we'll first assume that they are, and we'll show that this leads to a contradiction. If there is a bijection from the real numbers to the natural numbers, then let us list this bijection in the following table. On the left we have a natural number, and on the right we have a corresponding real number. If it happens that the number on the right is rational, then we can assume we have just padded it out with zeros to infinity. Now, I'll construct a brand new real number that doesn't appear anywhere in this table. We'll start with 0 and a decimal point. For the first digit after the decimal point, I'll take the first digit of the first row in our table. Then I'll add 1 to it. For the second digit, I'll pick the second digit of the second row. If the number happens to be 9, then it will just wrap around to 0. We continue this pattern with every row in our table. If we now think about it, the number we have just written cannot be any real number in the table. Why? Because it cannot be the first one, as the first digit is different, It cannot be the second because the second is different, and so on. It cannot be any number in any row because we've constructed it in such a way that it differs in at least one digit in its decimal representation. So already things are getting pretty weird. Now there are two different sizes of infinity. In fact, there are infinitely many sizes of infinity. Things can get very big. But for now, these two cardinalities for us will suffice, just thinking about countable and uncountable sets. I want to set up another fact that will be needed for the final result of this video. It's related to a property we call density. For example, the rational numbers are dense in the sense that between any two rational numbers there is always another one. For example, between 0 and 1 we have 1/2, between 0 and 1/2 we have 1/4, and between 1/4 and 1/2 we have 3/8. In general, we can find our witness by just calculating the average of our two rationals. And this continues on to infinity. No matter how close the rationals may be, as long as they are not the same, we can always compute a number in between them. This may not be surprising, but what I find surprising is that the rationals are dense in the reals as well, meaning that between any two reals there is a rational number. We know that rationals are countable and the reals are uncountable, meaning there are a lot more. This struck me as weird at first because I was thinking very finitely. What I mean is that if we imagine a finite case of density, for example, let us imagine 5 fence posts with 4 grass fields in between them. Some kind of finite definition of density would be that between any two fence posts we need to have a sheep. So clearly we need 4 sheep to place between the 5 fences, and everything is okay like that. We see that we need 1 less sheep to fit in between the 5 fence posts. But the rationals are not 1 less than the reals, they are infinitely less than the reals. In our case, if we remove, for example, 2 sheep, there is no way that we can fit these 2 sheep so that between any two fence posts there is sheep, no matter how we shuffle them. However, this analogy breaks in the infinite case, and the easiest way to see this is by imagining the decimal representation of two real numbers. If we assume them to be different, then somewhere along their digits there should be a difference, or else they would be the same. We can look through the digits and find the first place of difference. If we truncate the two numbers up to then, we can easily construct a number with finitely many digits after the decimal point, which is between the two. And if it has finitely many digits, then it must be rational. There are no distinct gaps in the real number line in which we can fit our rational numbers. As long as we have two different real numbers, there is a whole continuum of points in between them with no gaps. When we put a rational number in between them, those two real numbers are not the immediate neighbors of this rational. We can always find smaller and smaller intervals in which our rational number is contained. Before we can continue to the final construction of this video, first we'll need to introduce another basic notion of set theory called the power set. This is nothing more than the set of all possible subsets of a given set. For example, the power set of 1 and 2 is the empty set, 1, 2, and 1 and 2 combined. As you can see, elements of a set can be other sets, and we can nest like this to infinity. We can arrange the power set of 1, 2 in the following diagram, such that they go from the smallest, the empty set, to the largest, the whole set, and the arrow connections represent a subset relation. For simplicity's sake, I will omit the arrows spanning multiple levels in this diagram, but we can implicitly think of them as being there. Here is the same diagram, but for the set 1, 2, 3 instead. And here is it for 1 to 5. As you can see, things get big pretty quickly. A chain in this diagram and in set theory as a whole is a sequence of sets, each one of which expands the previous one. For our purposes, we'll be talking about strict chains, meaning that each set expands the other one with new elements and is not just the same set repeating. And the length of a chain will just be the number of sets in it. Here are some example chains in the power set of 1, 2, 3. In general, in the finite case, the longest chain we can create is one more than the size of the set we're starting with, because we also include the empty set at the bottom. For the finite case, I bet you can pretty easily convince yourself that the power set has more elements than the original set. But we can apply the power set operation to infinite sets as well, for example, all possible sets of natural numbers. This would include not only finite subsets of the natural numbers, but also infinite ones such as the even numbers, the odd numbers, the prime numbers, and so on. Turns out that the power set has greater cardinality than the original set, even for infinite sets as well. So knowing that the natural numbers are countable, then power set of the natural numbers must be uncountable. This can be proven in a very similar way to the diagonal argument we used earlier, so I'm not going to go into much detail here. Now let us imagine the same diagram for the power set we used for the smaller sets, but for the whole natural numbers. This will be some monstrous construction spanning to infinity as in its width, so as in its height. Here you can imagine that the first row spans to infinity with all the sets that contain one element. The second row is all the sets that contain two elements, and so on. While going from the top to the bottom, the first row is all the sets which have one element missing, the second row is all elements which have two elements missing, and so on. While here in the middle part there should be some infinitely complex system of sets which cannot really be drawn on the screen, but you can imagine that over there we can find all the other infinite subsets of the natural numbers like the evens and the primes. I bet that if you think about what is the longest chain we can construct in this diagram, you probably think something like, okay, so we start from the empty set and end in the whole natural numbers which are countable, so by our previous logic we can do a countable length plus 1, which should still be countable. So the maximum chain is countable and we can construct it by just going element by element until we construct the whole set. But amazingly we can actually construct a chain with uncountable length. Think about what this means. At every step of the way when we construct this chain, there are countably many elements from us to choose. So how could we possibly make uncountably many steps forward? Sure, all of the subsets of the natural numbers may be uncountable as we already said, but it's very hard to imagine that there exists an ever-expanding chain which also has the same length. You would think that the uncountability of the power set comes from the fact that the subsets can intersect in many infinite and interesting ways. But everything we talked about until now gives us a quick and easy way to build this continuum-sized chain. When we say continuum, we mean the cardinality of the real numbers, because as we said, they form a continuum with no gaps. So how do we construct this chain? Remember how between any two reals there was a rational number? Well, what if we do the following? To every real number, we will map the set of rationals which are less than it, which can be written also like this. This is actually one way to define real numbers in set theory called Dedekind cuts. Because between any two reals there is a rational, then this would mean that we have mapped a different set of rationals to each real, which gives us uncountably many sets of rationals. But look at how these sets are situated with respect to each other. For example, the rationals less than 2 also include the rationals less than 1, and similarly for any two reals R2 and R1, if we assume R2 is bigger, then it would contain all the rationals less than R1 as well. This directly gives us the chain of rationals which has an uncountable size. We just take the sets of rationals formed in the aforementioned way. But the original question was about natural numbers, not rationals. Well, we can fix this as well. Remember how the two sets have the same cardinality? We should be able to do it with naturals as well, and we can. If we go back to our bijection from naturals to rationals, we can just apply it in the reverse direction. And for each rational, we can restore its corresponding natural number. therefore transforming the sets of rationals to sets of naturals. And this reverse mapping doesn't break in any way the subset relation. Thus, from a chain of rationals, we have constructed a chain of naturals instead. Some of you may be wondering how exactly does this chain look like. Well, we can't really list it explicitly, after all it's uncountable. We just know that it exists, and we know how to construct it using some bijections. Here the chain itself becomes something dense, without a concrete starting and end point. Although we can always say that we put the empty set as the start and the whole set as the end. But in the middle of the chain itself, between any two sets in the chain there would be another, similar to how the real numbers are dense. This is a bit hard to imagine, because if we think about sets that differ by finite amount of elements, then we can find the one between them, which would be bigger than the first one and smaller than the second one. But now there should be a set between it and the first set. So continuing this logic will eventually lead us to two sets which differ by just one element, and there will be no way to put one in between them. But in our continuum chain, every two elements differ by infinitely many elements, so we can always put one in between them. This is because between any two reals there's not only one rational, but as we said, a whole continuum of points where we can fit infinitely many rationals. Maybe you can imagine this better if you think about something like the even numbers and the whole set of naturals. There are infinitely many differences we can make between them. So for example, we can make the set in between them to be the evens with every second odd number. Now there will still be infinitely many differences between the three sets, and we can continue creating finer and finer differences. But keep in mind, this process described here will give us just something countable. The construction with the real numbers gives us something infinitely more complex and uncountable. In the diagram, the chain would be passing in the middle in some infinitely complex way that cannot really be visualized. I like this result and think it's interesting. Turns out that even if you have countably many numbers left, the way in which you can choose non-intersecting subsets of these numbers is uncountable, and you can use these uncountably many choices to create a dense chain. I hope I was able to get across the main points and haven't totally lost you. I know this all can seem unintuitive and complex, but it's a fascinating area of mathematics that reveals the richness of infinity. This was my first video, so thank you very much for watching it. I created it inspired by 3 Blue 1 Brown Summer of Math exposition. I also recommend checking out this blog post by Professor Joe David Hampkins, which expands on the topic and served as an inspiration for the video too. I know there is a lot more to improve, like my audio quality, and I definitely wished I could have explained some parts of the video better, but I decided not to strive for perfection and just release it in the deadline, or else I might have procrastinated forever. I had a lot of fun making it, and I would appreciate any feedback you have. I have plans for at least a couple of more videos, so if you like this one, I hope you'll join me again soon.